Welcome to another lecture in compiler construction. So after we took a look at parsing top-down and bottom-up and different classes of bottom-up parsers, so LR, N, and LALR, and so on parsers. Now let's take a look at some practical issues when parsing, and also how to actually use a compiler generator or compiler, in this case the standard Unix tool YAC, to actually automatically generate a parser, a bottom-up parser, specifically an LALR parser from a given grammar. So today we're going to talk about practical parsing issues. One of the biggest issues when you want to write a usable compiler is to provide useful error recovery. So when you compile a longer piece of source code, you actually don't want to stop at the very first error you encounter. You want to give indications of all possible errors in the program to the compiler user. So you need to be able to somehow set up after a syntax error or something you discovered and continue compiling as if there was no error. Then there are specific problems concerning unary operators. We have to handle context-sensitive ambiguity, and we'll talk a bit again about left versus right recursion. And after that, we'll provide a quick intro into YAC. So we'll take a look at the syntax of YAC, grammar descriptions, and especially how the parser written in YAC and the scanner written in LEX interact. And of course, we'll also give an example for this. So, when you write programs, syntax errors are pretty common in program development. And our previous parsers were pretty simple. So, in the state diagrams for the scanners, we specifically excluded the error case to keep the diagrams more simple. And also in our scanners really, our parsers really stopped when they encountered the first error and just output, oh yeah, there's an error somewhere in your code, and that's it. So that's obviously not what a programmer would want, because then you'd have to run your compiler over and over again. Now today, of course, compilers have become quite fast because computers have become fast. But nevertheless, I think all of you would prefer to find as many syntax errors as possible in each compilation, so you can fix them possibly all at once. So what we want is some mechanism to recover from errors we encounter when parsing, and such a mechanism helps the parser to move on to a new state where it can continue parsing when it encounters an error. So we need to select a couple of tokens or words that the parser can use to synchronize the input with its internal state, so that it can find a point from where to set up parsing once again, to create another subtree of our parse tree, for example. And when the parser encounters an error, the first one or a subsequent one, it then discards the input symbols until it can find such a synchronizing token or word. And then it can start by resetting its internal state to a consistent state, and that is one that's consistent with the synchronizing word. So consider a language that is using semicolons as statement separators, which is pretty common. So if you have something like this, you can imagine that a semicolon doesn't happen very accidentally. So you could try to use the occurrence of a semicolon to indicate, oh yeah, we could set up our parser again after this semicolon, because maybe it was just this one line of code from the start of the line to the semicolon that had an error, and then we can still continue parsing it. So when an error occurs, the parser then calls the scanner. Like here, we have a call to a function func, and then our bracket is the wrong bracket. It's a closing instead of the opening one. So then our parser can call scan until it finds the terminating semicolon, and then it can continue parsing the rest of our code from there. So a recursive decent parser can simply discard words until it finds a semicolon, and the parser can return some fake success message like, oh yes, I've read this successfully, and by the way, I've printed an error message, but I haven't told you. This is a bit more complicated when you're doing bottom-up parsing in an LR1 parser, because, well, it discards input until it finds a semicolon. That's fine. But then it tries to scan back down the stack to find a state with a valid entry that has a goto. So a goto, when an input symbol S is there, go to a certain statement. And the first such state represents the statement that contains the error. So this resynchronization in LR1 parser needs to discard entries on the stack above that state to push the state goto onto the stack and then resume normal parsing. So that's a bit more complex than if we would just do top-down parsing. So another problem when building grammars for real programming languages are unary operators. So we've seen several different examples for a classic expression grammar, and we've seen, for the sake of simplicity, we have only included binary operators in most cases so far. But of course, you know, algebraic notation also includes unary operators, like a unary minus operator, or an operator that returns the absolute value of a given variable or number. But in languages like C, there might be other unary operators like the auto-increment I++, which just operates on I and increments it by 1. The auto-decrement does the same, just decrementing. We've seen the address of and dereference operator for pointers. We also have the Boolean complement operator, the exclamation sign. And we also have typecasts, which are round brackets around a data type followed by a variable name. And if we want to write a parser for a language that supports one or more of these features, adding these features to the expression grammar works, but it requires a bit of care. So let's take a look at a bit more realistic expression grammar. And this expression grammar not only has the usual arithmetic operations like plus, minus, multiplication, and division, it also has brackets here to group expressions together, so to define an order of evaluation, and it has something new, and here it has the absolute value operator, and we just write the absolute value operator here as 2 pipe symbols or 2 vertical bars. Usually you'd write the absolute value operator in mathematics around the variable name. We did it just using these 2 bars together to make parsing a bit simpler here. So essentially, when you want to parse an expression, you could, for example, try to parse an expression absolute value of x minus 3. Now you would need to think about what would this absolute value actually work on. So would it work on the whole expression, or would it just work on x? So if you're used to mathematics, I would say the absolute value operator just applies to the variable standing next to it, or in mathematics, the variable actually standing in between the 2 vertical bars. So if we want to enable this behavior of our parser, well, we have to just formulate our grammar in the right way. So for example, when you parse this here, you want to have your factor, which resolves to a name, which is an x, so that variable name here, your identifier. You want this to essentially resolve to a value, and this value is obtained by putting the absolute value operator in front of our factor, and then all the other operations here, like our minus and the 3 here as a number, are further up in our syntax tree. So this means we evaluate the absolute value operator first, and after that we evaluate the rest of our terms, so minus and 3. So the absolute value should have higher precedence than, for example, also multiplication and division, but it needs to have a lower precedence than our factor here, because we want also, when we have factors here, to have expressions grouped inside of brackets here. And of course, if you apply the absolute value operator to such an expression in brackets, so you write absolute value, bracket, some expression, closing bracket, of course you want to have the absolute value of your complete expression in here. So you want to have a lower precedence than factor. So this enforces the evaluation of parenthetic expressions before the application of our absolute value operator. And we can do it this way by just including it here. So either value is our absolute value operator and followed by a factor, or it's just a simple factor without the absolute value operator. This example grammar is still LR1, but we have a problem here. And this problem is that value in both cases just directly goes to factor here. So if we would want to write absolute value of the absolute value of x, this wouldn't be possible in this grammar, because the first time we read the absolute value symbol here as a token, then we immediately continue to factor here in our grammar, and there's no way to actually immediately express something like our value again. Now, of course, writing this doesn't make too much sense. The absolute value of the absolute value is an idempotent operation, so it still returns the absolute value operator. But of course, it's a legal mathematical operation, so why should we restrict our programmer in writing code? Maybe it's part of a more complex expression or something like this, or even a macro expansion. What would actually work is writing it like this. So you take the absolute value of x first, which is an expression here, which goes down here, term, value, absolute value. And then you put the brackets around it, and then you can take the absolute value of the expression in brackets here, because this would go from value to absolute value, the operator here, then going down to factor, resolve to brackets here, and the next expression would then just go down through term and value to have absolute value, factor, and a name here. Now, this problem doesn't only show up with our admittedly a bit artificial example of this absolute value operator, because in very many programming languages you would write the absolute value operator like a function, so ABS bracket something, but still it's also a problem for other operators. And one common problem in C, for example, so when you want to write a parser for C, is the dereferencing operator, so our star operator here, because the dereferencing can occur on several levels here, So if you have a pointer to a pointer and you want to dereference the value stored there, you just add two star operators, so two dereferencing operators to this pointer to a pointer here. And this, if you look at, C code that's out in the net somewhere, that's a pretty common operation when you want to, for example, dereference more complex data structures and so on. So how can we solve this problem of double operators and similar things? So one solution here is to add a dereference production for value. So essentially similar to our absolute value operator, now we also provide a dereferencing operator to our value production here. So we have an additional production here that has the star operator in front of value. We know the resulting grammar is still LR1, and now what would happen if we replace this operator, which we've written with this x symbol here for multiplication, in term resolves to term times value, with a star operator like it's done in many programming languages? Well, that would look like this here. So we have term resolves to term multiplied as a star operator with value. And this would still work here. So what's happening here is what we call in programming languages so-called operator overloading. So not only the multiplication operator is overloaded, but of course also for unary numbers we have an overloading of the minus operator here, which also serves as an indication of a unary minus. So the same approach would actually work if you want to implement a unary minus in your programming language, and that's something that you should obviously do when you want to operate on numbers. Nevertheless, trying to use one word to represent two different meanings can create some syntactic ambiguity. And this was very common in early programming languages, like maybe you've heard about them in, maybe today it's history books, like Fortran, PL1, or Ada. And why did the designers of these languages actually use this overloading of symbols? Now, in very early computers, you didn't have your whole ASCII character set, like with 7 bits encodings with like 3 or 4 different sorts of brackets. So you'd have round brackets, you'd have curly brackets, you'd have square brackets, and for example, you could also use a less and greater sign as some sort of angled brackets like in HTML. So in very early computers, you only had a very restricted character set because yeah, the amount of data you could store in a computer was very small, so you tried to restrict yourself to as few bits per character as you could realize. So very early computers maybe only had uppercase characters. So you see very old printouts of computer listings that only use uppercase characters, and they didn't have very many special characters, so just punctuation needed for writing texts and the digits, and that's all. So that was because many of the early input devices, like teletype devices, were derived from very early communication stuff. So really, wire telegraphy, which just, was very primitive. And so very early character sets maybe restricted themselves to only having 6 bits for character encoding. Some even only had 5 bits for character encoding and a special switch character to switch between 2 different interpretations. So there wasn't that much variation. And as a consequence, actually, these early designers of programming languages had to overload some operators, and one very commonly overloaded operator is the round bracket here, so the parentheses. And in Fortran, for example, they're used both to include a subscript expression of an array. That's what we use these square brackets in C for. And they're also used, as in C, as the argument list of a subroutine or function. So if our Fortran compiler would read an input phi, opening bracket, I, j, closing bracket, the compiler itself cannot tell if phi is actually a 2-dimensional array, which we want to access with row I and column j, or the other way around, or if this is a call to a procedure phi, which is passed the 2 parameters I and j. So differentiating between these 2 cases would require knowledge of the declared type of phi. So is it a function or is it an array? This information is not obvious from the syntactic point of view, so we need some additional information to be able to figure this out. Nevertheless, our scanner would have less problems with this because it just sees a character sequence here and it tells us, well, phi is some sort of name or identifier, and lets the compiler or the parser figure out what the meaning of phi is. Is it an array or is it a function? So how could we handle such context-sensitive ambiguity? Well, we can add productions that derive both subscript expressions and argument lists from a factor in our example grammar. So if we want to handle this in a classical expression grammar, that might look like this one here. So we have our factor here. That might be a function reference or an array reference or some expression in brackets or a number or an identifier, a name. And the function reference might resolve to, a name, opening brackets, an argument list, closing bracket, and the array reference would also resolve to name, opening bracket, argument list, and closing bracket. And if you actually remember our previous lecture, you've seen this is a problem for our scanner. And this problem occurs because these 2 final productions here for function reference and array reference have identical right-hand sides. So this means our grammar is ambiguous, so our bottom-up parser or our LR1 table builder here to create a bottom-up parser would then have a reduce conflict because it doesn't have any additional information to choose between reducing this one here to a function reference or to an array reference. So to resolve this ambiguity, we need extra syntactic knowledge. So we need to know is what is called name here. Is it actually a function or is it an array? Now in a recursive decent parser, so a top-down parser, the compiler writer could combine the code for function and array reference, and then add the extra code required to check the name's declared type whenever it has found out, it's a something reference that resolves to name, bracket, argument list, closing bracket, and then it could check, do I know anything about name? So this involves so-called symbol tables, and we'll talk about symbol tables later when we talk about type checking and things. And then our top-down parser, our recursive decent parser, could actually check, I've encountered this token with, the name. So is it a function, is it an array, or has it not been defined at all, maybe? And so it can decide which action to take. If you want to build a table-driven parser built with a parser generator, then of course you have automatic actions, so you can only choose a single, unique production somewhere. So the solution you have to apply to resolve this reduce conflict has to work within this framework that's provided by your table generating or compiler generating tools. So how could we do this? Well, in general, there's two different approaches to solve a problem like this. The first is the approach we've always recommended: rewrite your grammar. So rewrite the grammar again as for the just recursive decent handwritten parser, and just unify this name bracket arglist closing bracket pattern here on the right hand side, so this production, to indicate it's a function or an array reference. So whenever our parser now encounters something like this, it resolves it to function or array reference. So obviously this only defers the issue until a later step in translation. So when we have more information, so we can consult symbol tables, we can resolve this problem with information from the declarations of functions and arrays, and then finally figure out which code to generate for this expression. So shall we generate code to call a function, so push maybe these arguments on the stack here, and then find the function pointer for a function name and then jump to this location here? Or should we just do an array reference, which would mean to use name, for example, if it was some sort of C behavior, name as a base pointer, and then do something like number of columns type times number of rows plus columns, something like this, to generate code. Now, our scanner could be another way to solve this problem, because a scanner could try to classify identifiers based on their declared types. So this requires a bit more elaborate communication between the parser and the scanner. So essentially the parser would have to pass information on any data type declaration it has found, so a function declaration or a function prototype or an array declaration, back to the scanner, and the scanner would need to build up a table so it can return the correct token type here. So this of course only works as long as we can require symbols to be defined before they're used. So if you have a language that actually requires this, then that would work. And then the scanner could actually try to look up information about the symbol it scans, and then can find out, is it a function name or is it an array name, and return this additional meta information to our parser. So then these two productions here for function array reference, for example, would actually work without a problem here. So rewritten this way, the grammar would be unambiguous, since the scanner returns a distinct syntactic category in each case, and so the parser can distinguish between the cases. So we're still talking about practical issues when implementing grammars to parse a language. And one practical issue we've seen was if we have left or right recursion in our grammar. And we've seen that a top-down parser needs a right recursive grammar, because if the grammar was left recursive, it would just end up going through its grammar symbols over and over again without ever finding a resolution. And a bottom-up parser can accommodate either left or right recursion. So compiler writers must actually choose between left and right recursion in writing the grammar for a bottom-up parser. So how can a compiler writer actually decide if he or she wants to use left or right recursion? Now, one identifying criterion might be the stack depth. So if you use left recursion, this could lead to smaller stack depth. And if you have a memory constrained device, for example, you would have lower memory use, you would have fewer recursions here. So a left recursive grammar like list resolves to either list and some element, or just a single element here, would be easier on the stack on your memory consumption, whereas a right recursive grammar would need to go all of the elements and then finally remove all that stuff until we have resolved this to a list. So what happens when we use a left recursive grammar? So let's just take a quick look at the details of it, because I think that gives a bit more insight into what's actually going on inside your parser. So our left recursive grammar shifts element 1 onto the stack and immediately reduces it to list when it sees an element here. So when we parse something like this, next it shifts the next symbol element 2 on our stack, reduces it to another list, and then element 3 until we arrived at element 5. So our left recursive grammar, or parser for our left recursive grammar, proceeds until it has shifted each of the 5 elements onto the stack and then reduced them just to a single list. So our stack reaches a maximum depth of 2 because we have an element and part of the list on the stack, and the average depth would actually be 10 over 6, so 1 plus 2 over 3. So that's not a very high stack depth. So essentially our left recursion would look like this, and of course, since we've already have resolved all the rest of the things here, we just need to have these 2 elements, for example, on our stack. So the stack depth of a left recursive grammar depends on the grammar and not on the input stream. How does this look like for a right recursive grammar now? So a right recursive grammar tries to fit as many elements onto the stack, so it shifts and shifts and shifts. So essentially our stack looks like this. We start with a list, we find an element, okay, and there might be a list coming. We find another element, there might still be a list coming, and another element, a list, and another element, yet another list, and so on until it had reached element 5. So we have all these 5 elements on the stack here until we figure out, okay, now it's the end of our list. We have parsed successfully our complete list. So only after really pushing all the 5 elements onto the stack, then our right recursive grammar can start to reduce all of this back again to our list, and the remaining elements then using that production here. So the maximum stack depth here will be 5, the average stack depth will be 20 over 6, so quite a bit bigger even for this very simple example. Now the problem is that, well, of course you can build longer and longer lists. So the maximum stack depth, wow, complicated word, maximum stack depth that's generated by this right recursive grammar is not dependent on the grammar, but only by the length of the input list. So the longer the input list, the more stack space you'd need, and especially on early computers that really had like very restricted amounts of memory, so you had compilers for realistic programming languages like C or Pascal already on 8-bit machines with 64 kilobytes of memory. And so, of course, there the maximum stack depth was really important. So if you had a very long list you wanted to parse with such a parser, well, you may have run out of stack. So with several thousand elements in a list, this can definitely become problematic. Another problem that's related to left and right recursion is the associativity of expressions. So we've already seen that left recursion naturally produces left associativity, and again, right recursion, of course, then naturally produces right associativity for operators. Now, usually you'd say for most arithmetic operators, I don't care, but let's take a closer look. So in some cases, the order of evaluation actually makes a difference. So consider this expression here, x1 plus x2 plus x3 plus x4 plus x5. So the left recursive grammar here implies a left to right evaluation order, obviously, and the right recursive grammar would imply a right to left evaluation order. Now, for integer numbers, this usually doesn't make a big difference. Of course, you can also have like integer overflows, but for different number systems, especially floating point arithmetic, these two evaluation orders can definitely produce different results. So either you have something like this here, so you go left recursive or you go right recursive. So let's take a look why the results for such a simple arithmetic expression could actually be different. Let's consider a real expression x1 plus x2 plus x3 with values for x1 equals to 1.0. x2 is a pretty big number. We've already seen the scientific notation in the second theoretical exercise. So this would be 1 times 10 to the power of 10. And we have another number x3, which is minus 1 to the power of 10. So two very big numbers of the regarding the absolute value, one very large negative, one very large positive number, and a simple 1 in one of the variables. Now, if you have a left recursive grammar to evaluate this expression, would mean you would actually evaluate x1 plus x2 first. So if we write brackets to just really exemplify this, it would mean in brackets x1 plus x2, and then you take the result of this addition and add x3 to it. So let's look what comes out of this. Well, obviously, you would expect from your mathematical knowledge that x2 and x3, well, the one is the negative of the other, so the sum of these both here would be 0, so the sum would be 1. Well, not quite in this case, because the first thing we do is we add 1 to 1 times 10 to the 10th power. And this addition here is problematic in floating point numbers. And this is problematic because we only have a certain number of bits available for storing our floating point number, for example, 32 or 64 bits. And this means that we lose precision at the end where the least significant bits are stored. So this would mean that, depending on your floating point representation, that when you try to add 1 times 10 to the power of 10 plus 1, that the result is actually still only 1 times 10 to the power of 10, because, well, there is no bit left to store this least significant 1. So if you then add, well, minus 1 times 10 to the power of 10, well, you just get this one plus that one, and these obviously cancel themselves each other out. So you have an incorrect result of 0. In this case, if you had a right recursive grammar, this would imply a right to left evaluation order. So you'd start with the right hand side first here, x2 plus x3, which resolves correctly to 0 here. And then you have enough bits left to store your 1.0 because you don't have to store any values with a large exponent here, which gives you the correct value of 1. Floating point is a very complex thematic, so especially if you write numeric code for simulations, physics simulations or whatever, or even in gaming where you use floating point values, for example, for calculating, like if you hit a target or something like this, you need to take care of effects like this, because obviously these results should not differ. And if you're interested in details on this, we gave you a literature reference that contains more about floating point numbers than you ever wanted to know, I suppose.